that. I guess the more interesting thing, hopefully for next week, which people will come for, is this almost 9-page document on some practice exam questions. So basically there's some questions, you can have a read of it yourself when you have the time, when you're preparing for your examination. That these things will be, well, maybe slightly harder than you might expect, but at least they're at the level. And so there's complete solutions with all of them, so that you, if you're not happy with the questions, then at least you can see how to do them. There's a slight change in the notation. It's just these are my own questions for when I taught this course. So this is not consistent with the course, but I think it should be possible to follow what's in these. And basically for next week, hopefully more people will come and we'll go through the solutions in detail. Okay, so for this, just this kind of optional pieces of notes, what we were talking about was the idea of Bayesian statistics. So the notion is this, is just as we had for doing maximum likelihood estimation, we had a random sample, x1 up to xn, but in this case, they're only a random sample which are conditionally independent, given a parameter, a population parameter, which you want to estimate. So essentially, just as you had, or we had, of course, classical statistics where we're doing likelihood-based estimation, the likelihood function looks the same. And what we're going to do is we want to still create an estimate for this unknown parameter theta. For example, the mean of the data, the variance, and so on and so forth. But what we're going to do is, instead of using estimating, optimizing this function with respect to theta, we're going to use this mechanism of the Bayesian paradigm, which is associated to this Bayes theorem that we saw yesterday. Okay, so we covered this. So the idea is that Bayes theorem for this type of statistical inference is like this. So you have a likelihood function. This is the likelihood function which we already had in our classical statistics. And the idea is that before you see the data, you have a probability distribution pi of theta, which is called the prior. Okay. And the idea is that conditional on the observed data, we want to work out what is the random quantity pi of theta. Okay, and this is basically, this is just the Bayes theorem that you've seen yesterday, except the role of the random variables theta is conditioned on the observed data. And in fact, this is a more intuitive framework than your classical likelihood-based estimation, where one optimizes the likelihood function. Because if you remember going back to chapter 7 and 8, when we're looking at hypothesis tests and confidence intervals, a lot of our probability statements are made about the random sample, i.e. the data. But of course, when we observe data, typically what happens is that we know what it is. It's not a random quantity. We know what we have observed. So here the idea of the paradigm is to shift the randomness to the unknown parameter theta. Okay, so how can you estimate the theta? So this is just a random, there's a distribution of your unknowns. So how do you estimate the distribution? How do you estimate the parameters? One way, for example, suppose theta is a real valued quantity, you could compute the posterior mean. Okay, so this is a probability distribution. Pi theta given x1 up to xn is a probability distribution on your unknown parameter. And so you just average over the uncertainty of the distribution on the parameter of interest conditional on the data. Okay, and this is the way you could do that. And there are other things you could do. You could compute something called credible intervals, which are basically this Bayesian analog of confidence intervals. So the idea is that you try and find an interval, theta bar, under bar, theta over bar, such that the probability that the parameter lies within this interval is 0.95, and there's some other things like the fact that this distance should be small and so on and so forth. The key point is, if you remember, when we construct a confidence interval, we find a pivot which such that the probability that the data lies in that, the probability that the data lies in an interval associated with the parameter is of a pre-specified number. But it makes no sense to do that, because basically the data are not uncertain. We know the data. This is making more sense, at least in my mind, because this is a probability statement about something that I don't actually know, the parameter. Okay, and this is why, at least to some people, me included, when I studied it, is it actually has a more intuitive interpretation, as opposed to the likelihood-based scheme. But the key issue with this approach is the fact that this distribution, this posterior distribution here, this probability distribution, you can see that in the denominator, this is what's called the marginal likelihood function. Okay, so this is just the joint distribution of the observations marginalized with respect to the prior. Okay, this is the likelihood conditional on theta. I integrate out, and I get the joint. Okay, so this integral here, or if theta were discrete, this sum here, it may not be analytically tractable. So whilst what you're doing, I think, has a more kind of better, there's a better underlying theory, i.e. it's a better thing to think about. It's more computationally challenging because you do not know these quantities typically. And so, in fact, most of the people that do Bayesian statistics or have done Bayesian statistics in the past essentially become a type of numerical analyst where really you're doing computation of integrals. That's what I became anyway. Anyway, despite the fact that you don't often always know the posterior, there are cases where you can do the computations analytically, and we'll just look at a couple of examples just to see. Okay, so this is example 3.1. So basically we discussed that very quickly yesterday. So this is that the data xi is given. I know the rate parameter theta, which is lambda in this case, or IID exponential, and the prior on lambda is gamma. Okay, and what we want to do in this example is to calculate the underlying posterior distribution of this parameter lambda given realizations of the data x1 up to xn. Okay, so the way in which you can do this, so you don't need to do it this way. So this is purely computational. It's not important to understand the calculations, but what this collection of calculations are doing is to calculate the joint density of x1 up to xn, the marginal likelihood. So remember what that is. That's the likelihood function. This is the likelihood function you get for exponential data. And this is your prior PDF. This is a gamma PDF. And basically to get this marginal likelihood, we just want to do a one-dimensional integral. So this is pretty straightforward, this integral. You just take out all the constants. That's what we've done here. B to the a over this gamma function, which is the integral between 0 to infinity of x, 0 to infinity of x to the a minus 1 e to the minus x. Okay, and then this is what you're left with respect to the function lambda, with respect to lambda. Now all you need to do now to compute this integral is very simple, because essentially you're going to convert it into another gamma function. So what you can do, if you're interested, you just make the substitution u is equal to this stuff in here, lambda e sum I1 to nxi plus b. Okay, if you make that substitution, you get e to the minus u. The integral still goes between 0 to infinity. And lambda, of course, is equal to u over the sum of the xi's over b. So you get this extra term here, which corresponds to your change of variable in your integral and the Jacobian for transformation. Okay, it's just simply integration by substitution, which you studied in A levels. Okay, now, of course, this integral, you don't know how to analytically calculate it, but you can express it as a gamma function. So this is by definition a gamma function of n plus a. N is the number of data points, and a is a positive parameter, so this thing is a well-defined quantity. Okay, and that's it. And then to compute the posterior, it's very simple. The posterior, well, this is the likelihood times the prior. This is exactly the expression that you had, which was the integrand here. Okay, and the posterior PDF is just this term divided by the quantity we just calculated. So this constant is going to cancel. Okay, and this function here, you can recognize it if you do some thinking. This is the PDF of a gamma distribution whose parameters are now n plus a and b plus the sum of the xi's. Okay, so in this case, you can compute, for example, the posterior mean. The posterior mean is just the ratio of this one to this one. You don't need to know that, but it happens to be the case for any gamma distribution. Okay, and actually, if you work out the MLE for this example, that's in the case A is equal B is equal 0, so it's related to the MLE in this case. So this is a second. I think we've got two more examples. Let's have a look at that. So one more example. So here, the data now are divided by xi's are IID given lambda Poisson. So P means Poisson distribution with parameter lambda. And we suppose a priori the lambda is gamma AB. It's a very similar example to the one we had before. So in this case, the likelihood function, well, this part, lambda to the sum of the xi's, e to the minus n lambda, 1 over, this is all coming from the likelihood function, and this is your prior. Okay, and this integral is very similar to the one we did before. All you need to do is you just take out the constants. So it's this one and this one. These are constants in lambda. And basically now this thing is almost the same integral as before. Of course, the power of lambda is different than we had before, and the power of this thing is different, but it's the same technique. You make the substitution u is equal lambda n plus b, and you get e to the minus u. Lambda, of course, is equal to u over n plus b, so you'll get this factor here, which comes from the substitution and the Jacobian, and then you have this thing, which is basically a gamma function, so it's gamma, the sum of the xi's plus a. So that's the likelihood, marginal likelihood function, okay, which is not important in some sense, but you can calculate it. And now the posterior PDFs, the likelihood times prior, that's just this thing here, okay, that's what you get there. And now the posterior is just this function divided by this function, and of course you get some cancellations. These things cancel in the numerator and denominator, and basically this is your posterior PDF. And it turns out, again, if you look and you check, that this is the functional form of a gamma distribution. Again, with these, this is the parameter A, if you like, and this is the parameter B. Okay, and so you can compute an estimate of the parameter lambda by computing the posterior mean. The posterior mean for a gamma distribution is just this one divided by this one. Okay, and if you take A and B equals 0, and you have a look at my additional notes on MLEs, you recover the maximum likelihood estimator. Okay, so this one, well, we'll go through it. It's a little bit painful, but anyway, it's not so difficult. So in this case, what we're going to suppose is that the data now are xi's IID with their Gaussian with mean mu and variance 1. Okay, and we're going to make a prior on mu, which is normal, with prior parameter xi is the mean, and this is the variance kappa. Okay, so now what we're going to do is we're going to compute the posterior distribution again, and it's very similar. The thing is, we're going to compute the marginal likelihood. So the marginal likelihood is the integral over the space, so the mu is a priori normal, so the space is minus infinity to infinity. This is the likelihood function, and this is the prior. Okay, and so basically we want to compute this integral with respect to mu, and the trick here is basically to rewrite the integrand of the form e to the minus mu minus some parameter alpha squared times 1 over 2 beta, because basically it's a Gaussian type integral and one knows how to do that. So basically this calculation, which looks really horrible but it's not that difficult at all, is just trying to rewrite the integrand in the case of a Gaussian. Okay, so basically to do the integral, so you just take out the constants, that's what you do there, and you're left with this. And now the thing is we want to play around with this exponent so that basically it's of the form, so there's only two of you here, so I suppose I could write it. Oh, there's no pen anyway. You just want to write this exponent in the form, so just, I'll go through this, but basically at the end you see you get something like minus 1 upon 2, a constant mu minus another constant all squared. That's what we're trying to do. So basically we look at what's in the exponent, which is this. Okay, you can multiply out the brackets. It's not very difficult, and if you do, you'll get something like mu squared n, that's going to come from this one, and 1 upon kappa, which is going to come from this one, minus 2 mu, and you get this one, this is I over kappa is from this one, and the sum of the xi's is from this one, and then you get some extra stuff, which we don't care about ultimately, because they're only going to depend on, they're not going to depend on mu, and we're going to integrate it with respect to mu. Okay, so we make the notation, this thing on the end is this function c. Okay, you get minus 1 upon 2 here. So then basically now this thing, we're still in the same position, so this is not changed, and this thing on the end is c. Okay, so now what we're going to do, all this calculation is doing now is to complete the square. So what you do is you take out this factor n over 1 plus kappa, you take that outside, and then you complete the square. So you get this thing, and you get this is the remainder from the complete the square, and this c is all the same before. So nothing more than that. Okay, so now again, we don't care about this part, so we'll just absorb it within C. So C prime is now C plus this extra bit on the end. Okay, so now what we've done is we've shown that the integral, so this is just dealing with the exponent we had in here. Okay, so basically using this equation that we have here, and using this notation here, the marginal likelihood function is basically, well, this is the stuff we had outside. This exponent comes outside because of this thing does not depend on mu. And inside our integral, we have still the integral from minus infinity to infinity, exponential, and basically it's this part here. Okay. Now this type of integral I can compute, right, because this basically, this thing here is the unnormalized density function of a Gaussian distribution. Okay, so what it means is that this integral, it can be computed exactly because it's just equal to root 2 pi, and it's divided by basically the square root of this variance. Okay, this variance is 1 over this. It's divided by this factor here, square root. Okay, it's just using the fact that a Gaussian integrates to 1, and this function here is basically a Gaussian PDF up to a normalization constant, and this is 1 over its normalization constant. Okay. So in the final scenario, all we've shown is that the joint density of the observations is basically equal to this function. Okay, and we've absorbed some of the unpleasantness of these terms here. So this, for example, these terms and these terms have absorbed into this C prime. Okay, so then the posterior distribution is basically the likelihood times prior divided by the function we just computed. So this is the likelihood times prior. It's basically, it's this function here, except without the integral. Okay, and so then basically we get a nice cancellation because these things will cancel in numerator and denominator, and you get basically the posterior distribution looks like this, and that's the density function of a Gaussian distribution where the mean is basically this and the variance is basically 1 over this. Okay, so the interesting point is basically the posterior distribution is in the same class of distributions as the prior. So the posterior mean for mu, I've written capital Xi here for some reason, it looks like that. That's the posterior mean, it's this thing here. Okay, and again, if you let kappa equal, Xi equals 0 and kappa go to 0, infinity, sorry, then basically you're going to recover the maximum likelihood estimator again. Okay, so the interesting thing about these problems, so in the first one we had exponential data, gamma prior, gamma posterior. The second question we have Poisson data, gamma prior, gamma posterior, and the third one normal data, normal prior, normal posterior. It's not by accident that the class of distributions for which the prior belongs to and the posterior distribution are the same, because this is something called conjugate priors. Okay, this is basically the crash course introduction to Bayesian statistics. Okay, but the key point is basically now what you're doing with, instead of doing optimization, you're essentially doing integration, and actually the latter is more difficult than the former in general. Okay, very good. So just a couple of more examples, and basically that's all I prepared for this week. These are just some more examples on conditional expectations, and actually rather interesting examples because they don't come from nowhere. They're actually pre-specified examples which appear in actually the theory of stochastic processes. So again, if you're ever interested in learning more probability theory, then these things will come along. So just some examples on conditional expectations. So here what we have is an infinite sequence of IID random variables. Apparently they're discrete. Independent identically distributed random variables, discrete, and they have a finite mean. Okay, and then independently of this sequence, I take a parameter capital N, which is a random variable, which it could be 1, 2, 3, up to infinity. And again, it has finite mean. And in this example, what we're going to compute is this expectation of this sum. But the key difference between the things we've done before and the thing what we're going to do here is the number of summands, capital N, is a random variable. Okay. Now, why is this interesting? Well, it turns out that this is a kind of special case of something called a compound Poisson process. If you were doing tutorial 8 today, you would have seen a Poisson process. And this is basically something associated to this. So it's not that I've just invented it. It turns out that computing this expectation is important in some problems. Okay, now the key point is we know if capital N was a constant, we know how to calculate this expectation because basically we can rewrite this in terms of mu. So suppose capital N is fixed. So N is fixed. I don't know why I wrote this, but N is just some number in the set 1 up to infinity. Okay, so I take this expectation. Now I know how to calculate that. We've done that before, right? So the expectation of a sum is just the sum of the expectations. So this is the expectation of x1 plus the sum I is 2 to n of the xi's. I do the trick one more time. Expected value of x1 plus x2 plus the sum I is 3 to n of the xi's. So if you do that at n times, you get n times the sum I is 1 to n of the expected value of the xi's. Okay, we did this result in lectures. Now, the key point here is that we know the expectation of the xi's are all equal and equal to the expected value of x1, which is mu. So that is to say that basically the expected value of this, the sum i's 1 to n of the xi's is n times mu if n is a fixed number. Now, what we want to do is we want to now compute the expectation of the sum of the xi's, but capital N, oh sorry, yes? It means that basically x1, x2, x3, dot, 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 they all have the same probability density function, or CDF if you like. Yeah, they're random quantities which are independent of each other and have the same distribution, yes. Okay, so what we want to do now is we want to calculate the expectation with n random. So we know basically the expected value of the sum of the I equal 1 to the xi's. If n is fixed, right, so if I condition on that value, I get n times mu. So we know how to calculate things now, because we know, this is something we saw yesterday, that if I want to compute the expected value of the sum I is 1 to capital N, where the n is random, I can say that's the same as the expectation with respect to n, and I take the expectation of this given capital N. Now, given capital N, this is just equal to capital N times mu, and now I take mu outside, which is a constant, and so the expectation of this thing is just the expectation of x1 times the expectation of capital N. Okay, and you can use this result for problems where you need to know these things. Okay. All right, let's have a look. So this is just one more example, basically something more on conditional expectations. So just in case, it's probably actually useful to know these things anyway. Right, so if you take three random variables, x, y, and z, they're jointly defined, and I take constants a and b, finite and real constants. Now you can note the following, that the conditional expectation of a given x or y or z, for a is a constant, is always a. The conditional expectation of ax plus by given z is just equal, as you have for ordinary expectations, a linear combination of those conditional expectations. If x is always non-negative, then so is its expectation. That's important to know. And if x and y are independent, then the expected value of x given y is actually equal to the expected value of x. Okay, and there is also a conditional variance formula. If you're interested in the variance of x given y, that's what you might expect it to be. The expected value of x squared given y minus the expected value of x given y all squared. So these are the nice, because basically all these definitions that we learn for expectations, that they port over to conditional expectations, at least almost surely. Okay, so this is just a computational example of using these type of results. So this example 2.3.34, that's actually from my own lecture notes, but we've seen this example before. So basically y is Poisson lambda, x given y is binomial np, and we'd shown that x given x marginally is Poisson lambda p. Actually, as I said, this was in last year's exam, last semester's exam. So we want to compute the expected value of x given y given x squared, expected value of x given y, and the variance of x given y. Okay, we know the following things, that if z is a random variable which is Poisson distributed, then the expectation of z is equal phi. So now then that means that the expected value of x, well, that's lambda times p. Just read that off. We also know if z is binomial np, so if you're doing tutorial 8, you know that the expectation of z is n times p, so the expected value of x given y is y times p, because y given x given y is binomial np. N, this is y, I think this is y. Yeah, this is y, not n. Okay, and for the expected value y given x, we did that. Yesterday. Actually, it's lambda 1 minus p plus x. Now, basically, if you want to compute the conditional variance, this is really what we're doing here. Here, what I'm doing basically is just a task in computing moments of binomials, and this is really what this is all about. So x given y is binomial yp. So if I want to find the expected value of x squared given y, by definition, that's the sum over all x's. So x goes from 0 to y of x squared times the conditional PMF of f of x given y. And f of x given y is this, it's binomial yp. Okay? So now what we want to do is we want to compute this. It's actually not so obvious how to do this, and I'm just going to show you how to do that. If you're interested, and you can check these things after class if you want. So here what you can do, you can take 1 minus p to the y outside. So I've still got x squared, y choose x, and then I have p over 1 minus p to the power x. Okay. Now if we make a substitution that u is equal p over 1 minus p, it's certainly, so this and this basically becomes x squared times u to the x. And you can show that x squared u to the x minus 2 happens to be equal to this. Okay, you can check it for yourself. This is not a difficult calculation to check. All right, you just have to find the second derivative of u to the x. So if you want to differentiate u to the x with respect to x, you can remember the first derivative is the log of x minus, yes, I think it's the log of x. No, it's not, it's something else, but it doesn't matter, log of u. So the expected value of x squared given y, so I make a substitution, so this is x squared times u to the x. So I then make this, I take 2 of those outside, okay, so I get u squared here, 1 minus p to the y, and then this one y choose x was already there, and now I use this substitution, okay. Right, okay, so now how do we do this? Now basically, if I have 1 minus p to the y times u squared times this one, x u to the x minus 2, it actually happens to be the mean, this happens to be the mean of the binomial, so I get yp. Okay, so the only challenge is basically computing this part here. Basically, now how do you do this? So this thing, this is like this. So basically what you can do is you switch the order of differentiation and summation. So I take this second derivative outside the sum, and now I just have to compute this sum. Well, this one is just the definition of a binomial expansion. So this is 1 plus u to the power y, and I just have to differentiate that twice with respect to u, and if I do that, this is the formula that you get. Okay, so basically now what I do, so this part times this is y times p. This summation is like this, so I just multiply it through by this factor. So 1 minus p to the y u squared, okay, multiplied by this term here, and then this one is plus yp. Okay, and then you make a substitution. U, remember, was equal to p over 1 minus p. Okay, and so if you make that substitution and do a little bit of algebra, this is the second expected value of x squared given y. Okay, so the variance of x given y is basically equal to this term minus the conditional expectation of x given y all squared, and this thing here was yp, so you get yp all squared here. So if you do a little bit of algebra, the conditional variance of x given y is y times p times 1 minus p. Now that's not surprising, so if you didn't like that calculation, the key point here is that x given y, right, is binomial y, this is a y, so binomial yp. So the variance of a binomial is n, well in this case is y, times p times 1 minus p. Okay, and again, if you're in tutorial 8, you did that today, or I did it today, we used exactly that result, and I had said in my tutorial that this is a painful calculation, and I've just shown you why it's a painful calculation, because this is not a set of algebra that you really want to do in practice. I mean, you can do it, it's not so hard, but it's tedious. This is just basically just doing calculations and algebra, and this is not a class in algebra. So I just wanted to show you that some of the things that we skipped in class are because they are just, this is not even, this is first year. If you're a math major, this is first year math, but we're not trying to make you mathematicians, we're trying to make you learn some probability and statistics. Okay, so that's all I had for the additional notes. So again, just for the hopefully next week there's more than 2 of you, but if there's only just us 2, then we can we'll do this on the board. Okay, so if there's only 2 of us, and then I will spend some time. But basically, these are the questions. You should be able to do most of them given the material that we've covered in our lecture course, and also the tutorials. There are some, I haven't got some questions on, for example, I don't have any questions on hypothesis testings or confidence intervals, but those are all covered in your tutorial classes, because I didn't really teach that when I did this class. So hopefully these things are useful. If you can do these questions, especially if you're watching a video, if you can do these questions, then you shall have no fear in the exam, because it might be a little bit harder than you see in the exam. You might notice this one was in your midterm because I wrote that question. Don't worry about these additional notations, that they're mine, but I don't think that would be too difficult to follow. Okay, so that's all I had, and hopefully I'll see more than 2 of you next week. Thanks very much. Yes. Yeah, the thing that I just said, the thing that I just showed you there, I've got it. Yeah, that's in, I sent an alumnus message this morning, so if you go to alumnus in the folder tutorial questions, it's in there. Okay, thanks.